formalization. This one is more like the implementation of the theory. And this is a joint work with Takafumi. What is monadic equational reasoning? It extends equational reasoning to monadic computations. And it was originally proposed by Gibbons and Hines in the same conference. And how it works, basically it combines pure equational reasoning, which you probably have an idea what it is, with monadic laws. And the basic idea of equational reasoning is that the programs are the specification. So if you want to prove that the program follows the specification, it will be equal to the specification. Okay, and it had been implemented in Rock, it was Rock at the time, by the Monae library, which essentially provides a hierarchy monadic interfaces. You see a difference with just monads. It allows to check the correctness of the reasoning and also to check that the laws themselves are correct. Those are the two aspects you want to check. Okay, I start with an example of the kind of equational reasoning we can do in Monae. So first, well, you have to introduce monad, and the monad is just an instance of the monadic interface. So I have a monadic interface corresponding to the exception monad. And this means that M is a monad that satisfies the laws of an exception monad. But it doesn't have to be the exception monad itself. It could actually extend it. And what I'm going to prove is that the fast product, which is basically a shortcutting product, it's repeating, basically, it's adding all the elements in the list S, and it's multiplyable elements in the list, and it will stop if there is a 0, and then return 0 in that case, okay? And I want to prove that it's equivalent to just computing the normal product, and as kind of usual when we are doing equational reasoning, there is an intermediate step which is saying, okay, something is going to be equal to, if there is a 0, I fail, otherwise I return the product. And okay, so I start from first, and I'm going to rewrite, and all the rewrite steps are written in Rock directly. So just first extend the definition. Then we are going to use the universality of fold R. Basically, it's I'm saying that I'm going to replace this part by the failed product that I had just defined before. Of course, if I do that, I have to prove that they correspond. Well, here I will this suppress the easy goals, so the base case is trivial, but this I will have to prove, that I will prove on the next slide. So I'm going on, so I've replaced this by prod, going on with the proof, again, expand prod. Then I can just do rewriting to extract the conditional. Leave the conditional out. And then I have things that are basically computation inside the monad. Catch of fail and catch of red, but those are monadic laws exactly. So I can just rewrite, which I reach this goal, and here, okay, I have to do a case analysis because it's the end of the story. If I do a case analysis, you can recognize that I'm trying to prove that it's equal to product S. So, in case it's not in the list, this is trivial. Otherwise, I need to prove it under the hypothesis that 0 is in the list. But I have a lemma that says that okay, if it's 0 in the list, then the product is 0. End of the story. And no, next I need to prove that one. In that case, actually, it's an equality that I want to prove. And I'm going to rewrite on both sides. If I expand everything, I get this kind of goal, and you can see that on both sides actually there is this case analysis of whether n is 0 or not. Just do the case analysis. Well, the base case, well, if n is 0, actually you see that I have failed on both sides. So that's solved. If n is not 0, then here I have the remaining part, which is an if. And on this side I have f map of the f. Okay? Which, again, I can leave to the if. because F map is just a function. And from now on, I will be rewriting the right-hand side, so then I get something like that. And again, same thing, I can use the monadic clause for F map, so that I get this, which is actually exactly the same thing as the left-hand side, so end of the proof. So this is the kind of proof we'll be doing. Of course, so we only allow correct steps, these proofs. But, so in practice, there are two sources of errors. Applying laws incorrectly, protecting against that. But using inconsistent laws could be even worse. And when we have many monads and many theories, actually this can become a concern. And there's a well-known example, which is an example in the paper I cited that I gave an hint, that comes in two steps. It comes first from a remark that the probability monad admits the right distributive of bound, okay, which is this law. Well, you don't have to look at the detail. We are here, this is actually a probability between the two possibilities. And the geometry convex monad, which extends the probability monad with nondeterminism, which itself is well defined. But that monad does not satisfy this. So you have to be kind of careful, because it's not because a monad extends another monad that it's going to preserve the law. Those are two independent problems. And a funny thing is happening is actually it's possible to create a monad that combine the two and is still satisfy this law, but then there are only degenerate models, so it's not really interesting. Okay, but what it really means is that one has to be extremely careful when building a hierarchy of interfaces. And on the hierarchy, we are building, because the monadic hierarchy here, actually I'm just showing the ones that are cited in the paper. So this is in the JFP paper this time. There are actually many more interfaces in the monadic hierarchy. And the important things is that it's considered, well, the interfaces, they are both monadic operations and laws. And for every leaf node, you need a concrete monad that instantiates it, and that proves that all the laws are valid. If you have a leaf node, then of course it implies that everything above it will also be consistent. Okay. So why is the hierarchy so complex? Well, one reason is that we need all these intermediate nodes to allow subsets of axioms. As I said, some combination may only be valid with less axioms. So it's not because the concrete monad allows more axioms that you could put them in the database. And the other reason is that we need explicit nodes for all usable combinations. Because contrary to type classes, when you write program with this hierarchy, you cannot use conjunction of constraints. You must use an explicit nodes. And again, this allows to ensure that all use combinations really have a node. You can just write your code supposing that this exists, and at the end of the story, actually it doesn't exist. And the other point, compared to actually other libraries doing this kind of things in Rock, for instance, we use abstract models rather than concrete ones. Which, well, there are two aspects. One, it avoids to depend on implementation. I think that's already an important thing. And in our experience also, this means that the code is polymorphic. And if you have that many interfaces, it becomes important because you want to use it at any lower instance also. Another remark actually of all this approach, of all these hierarchies, that closely follows the presentation of algebraic structures in mathematics, which is a pretty natural thing to do. Now, how are we going to build the hierarchy itself? So let's see just a small example with the hierarchy of the nondeterminism monad, which combines failure and alternance, multiple possibilities. Well, at the beginning, we first need to define what is a monad. And we define a monad from a functor. So first, you define a mixin using hierarchy builder, which is a tool for framework. So a functor is well, the first part operation combined with both. Technically, in a hierarchy builder, this is just a mixin. So to turn it into a usable node, you have to make it a structure. Then you can build a monad, which has more operation, right, join bind, and more laws. Then we'll go on to defining monad fail, monad out. And when you want to define the monad non-det, actually it's defined as inheriting from both from monad fail and monad out. And why the other reason actually you want to have these joint nodes is that you might want to add more laws. You're not adding a new operation, but you're adding laws here. Okay. And okay, so that's how you start your hierarchy. And what happens when you want to extend your hierarchy? Because you know you're going to try to prove some things, but it might happen that actually the combination you need is not in the hierarchy yet. And what you can observe is that actually there are two ways to do that. And there's some an approach which is I would call interface-driven extension, which is the most common one. It's that, well, the monadic laws are already well defined, so you can go look at the paper, and so you're going to add the operation of laws incrementally, depending on the different extension you want to consider. And you need to add, of course, models for each leaf. But there's also another approach, which might be less usual, and that I will describe a bit more detail later, is that, well, you have some concrete monad. You built the monad, but you don't really know its laws. So it's more kind of experimental. So you infer laws from the monad. You can prove them in the monad. You add them to the interface, and then you test them proving example. And if it's not enough, well, just define the laws and do it until you have something usable. And maybe you can try it then to prove that it's a meaningful set of laws. Next, as I said, every time you add a new node, you need a model. And what does it mean? So during extension, so it's newly familiar model for soundness, and also one much register it as an instance for each parent. And there are tools to help that in monad. One is that you can use monad transformer to create new concrete monads from existing ones. And the other is that you have a mechanism in hierarchy builder, a mechanism of factories, which allows to simplify the instance registration because it can be clumsy to have to add it for every part. And also, we observe that many models can actually be shared between several interfaces. So, in short, for instance, if you consider just when you want to create a monad, you don't have to go always through functor. Actually, you have another interface which says, okay, if I have read and join, which certifies some number of laws, then it's a monad. Or maybe more usual for people here, if I have a read and bind, then I have another set of laws that I must satisfy, and then it's a monad with join, etc. That can be used in context. Okay. And next, for monad transformer. For monad transformer, actually, what was done in the joint work with Nova is formalizing just kind of modular monad transformers. And in practice, implementing those monad transformers that can be then freely used to combine with existing other existing monads. And what is guaranteed if you do that is the result of monad transformer is going to be a monad that satisfies the interface specific to this monad transformer. Moreover, in some cases, you can also leave the operation from the original monad. for instance, if M is a failure monad, and you apply the state monad transformer, then the result will again be these operations, the lifting of the original field operation. Now I'm going to present a few examples. First, there's a quicksort example that you can see in the paper, which is based on Moore and Chang's deriving monadic quicksort. It's interesting because the idea here is that you use nondeterminism to give a specification sort, so it's a new way to give a specification. And usually when you do monadic equational reasoning is just proving that the program is equal to the specification. But here, of course, if we need nondeterminism, the specification is wider than the program. So this cannot be the case that the program is equal to the specification. But what we can do is encode the refinement, the notion of refinement, in the equality. So if the way is saying that M1 refines M2, program M1 refines M2, is the same as saying that the non-deterministic union of M1 and M2 is equal to M2. That is, it means that M1 is already actually included in M2. And then what do we prove? Well, first define slow sort as just taking all the permutations of a list and then checking, just keeping those which are sorted. And then we can compare quicksort, an imperative version of quicksort with slow sort in this way. That is, I write the list excess to an array. This is why I need an array plus monad here, starting at position I, and I apply I quicksort to that array. And this is going to be a refinement of doing just a slow sort and writing just the result of the slow sort. Okay. So this is a way to prove things. And if you look at the paper, you realize that actually it's quite tricky to do that. And one of the reasons it's tricky that you need lots of interfaces to look at all these results. Okay. Another application is, as I said, well, the type storm monad is a monad that was designed actually to represent OCaml stateful computation. That is model for ML references. It's used for the translation of OCaml programs. And well, what happened is that we looked around for possible well-known monads representing that, because this looks very similar to the Haskell but actually there is no equational theory for those. There is actually one there was one recently proved, but it's very technical. And what we're doing here to make computation easier, actually, we're using dynamic types. So I think it's a bit different from what they are doing. So we need to represent ML types. Since we have dynamic types, store access may fail. So the result is that the monad we are going to build, actually it's the last line here, is apply the state monad transformer to the option monad. The option monad itself is an instance of the same monad. Okay? And in order to make this work, we need this notion of defining what is an ML type and a translation from ML type to Coq type, which will allow us to define our store. A store, well, the cell in the store is just a type and the value of this type, which is defined by this Coq type function. But okay, this is the concrete monad, but we need to abstract it. And to abstract it, we first need to abstract the universe. That is, the notion I've given of ML type, actually it's going to depend on the program you're trying to encode. So we want to be able to change it. And we can define a ML universe of something that's parameter on the definition of the ML types. And then as a function code type from ML type to type, and you also need a type that you know is non-empty. And from this, you can define the ML universe, which packs everything to universe. You have the ML type, the code type, and also the fact that ML type is quasi-decided equality. And this gives us actually this interface for the type star monad with operation what new get put, and a large number of laws. Either some can be derived from the array monad, some other are new, because the new operation is a new one. And we test it by proving a number of examples. Okay.
You should stop.
Okay, I stop. Okay, and then I go directly to the conclusion. So monad is an accessible hierarchy of monad interface and models that allows to do monadic equation reasoning and can be used as a workbench for new monads. As recent development, we have built a complete Elgot monad for while loops.
Okay, any questions? Yeah?
And development. I've been using this, I guess, in Rock, and this library is very cool. The question I have is, I suspect there are two kind of different ways to reason about monadic computations, and one, that's what you describe, is equational one, which allows to prove refinement, and then also, as I know, there are like works to do like for logic, and then another way is like more kind of F star, where you reason about monads by generating well weakest preconditions, and then kind of get the formulas and then send them to SMT. So what's your take on like these two different ways to reason about like monadic computations, like the equational one and the one based on weakest preconditions? And yeah.
Well, actually, I do not have much experience on the other one. And I'm afraid people using the other one do not have much experience on this side either. So this ends up being difficult to compare. I just got this comment by Kenji Mayer, who is considered to be a specialist of the extra monads, that in the end you're doing more or less the same thing.
Yeah, it's very similar.
But in my experience, this side requires more preparation actually. You should be more careful about
Mm-hmm. Okay, yeah, thank you.
Right. Any more question? Yeah, a very quick one, please.
Yeah, very quick one. Sorry, it's not going to be about the talk, it's just about the very last line. Because I'm a big enthusiast of complete Elgot monads. So what do you mean by modular by simulation, maybe? You could say briefly. Okay, yeah, thank you.